All right. Thank you so much for joining us today on another edition of our Liftoff webinar series. My name is Joe Steele. I'm the Senior Director of Communications and Legislative Affairs here with Lyft. Thanks for taking time to join us today to hear a little bit more about VRC metal systems and the cold spray process with some of the fundamentals and applications behind that process. I'm excited to hear what is new and innovative with the cold spray technology. So a few things on the housekeeping list of items before we get started. Everyone should be muted, but if you are not, please take the time to do so now to avoid any background noise. This webinar is being recorded, so if we can eliminate as many background noises as we can, that'll make for better future viewing. So if there are folks who you think might be interested in this presentation, or weren't able to join for whatever reason, we did reschedule this from last week. So if we weren't able to join us today, please share that with them. It'll be posted on our website at lift.technology a little bit later today. You'll be able to find it in the news and events section of the site. So before we get started with VRC, I do want to tell you a little bit about Lyft. And if there are questions during the presentation, please use the Q&A function that is available on the Zoom toolbar, either on the top or the bottom of your screen. You don't need to use the chat function. You can use the Q&A function. We can address those questions after the presentation goes forward. So with that, I do want to share a little bit with you about Lyft, who we are and what we do before we hand it off to Aaron from VRC Metal Systems. So Lyft is a national manufacturing innovation institute, one of 16 around the country. We're a public-private partnership between industry, academia, and government. And our mission is to drive American manufacturing into the future through technology and talent development. We're a membership-based organization, pleased to have VRC as a member, along with 300 other organizations around the country, all focused on this goal of driving American manufacturing into the future through technology and talent development. And we do that through what we call smarter manufacturing, because we know as we move forward, our national economic security, resiliency, all rests on the manufacturing sector. And the next region, next area that tackles smarter manufacturing first is going to come out ahead. And as a Department of Defense Manufacturing Innovation Institute, we certainly want that to be the USA. So what do we mean by smarter manufacturing? We mean that we look at manufacturing holistically, looking at materials, processes, systems, and talent together. And so the connection between all three of those things, we lean heavily here at Lyft on materials research, manufacturing process, and the digital transformation those systems look like going forward. And we, of course, need the talent that runs underneath all of those. So at Lyft, we run two programs at Lyft. Our technology program, Leading Innovations for Tomorrow, and our talent program, Learning Innovations for Tomorrow. So a little bit about the technology program. That is, again, around connecting materials, processes, and systems. These are our four pillars of technology. All of our technology programs fall under one of those pillars one way or another. A little bit deeper dive into those here. I'm not going to quiz you on them, but as you can see, the breadth and depth of the work that we do, both in-house here at our Detroit facility or throughout our ecosystem around the country. You can see everything from the digital side, the ICME and computational materials engineering, to advanced alloy and process development, to agile and smarter manufacturing. It's where cold spray lives. As you see there, the second bullet down under agile and smarter manufacturing, along with multi-material joining. We're developing these new alloys, these new processes. How are we going to join all those materials together? On the talent side of the house, again, we want to make sure that we are enabling the talent and the exciting the next generation of multi-skilled manufacturing technicians around the country. This is still, again, around innovation, but it's really around new tools, new pathways, and new venues. We have our Ignite Mastering Manufacturing curriculum, which is a high school curriculum. So we start students and educating them and exposing them to the world of advanced manufacturing as early as high school. That is a 3-year program that we run out of our Lyft Learning Lab here in our Detroit facility and also around the country. It is available in a dozen states around the country. About 3,500 students around the country are currently participating in Ignite. Again, starting with material science and introductions to advanced manufacturing, then more into advanced manufacturing systems, and finally a capstone project by the end of their third year. I mentioned that we run that out of our Lyft Learning Lab. You see the description of the Learning Lab. It's really made up of 7 different labs, which include our Welding Technician Training Center and our CNC Operations Training Center, because we do offer those as programs, as certification programs for our adult learners. You'll see their Lyft Certified program, as well as Operation Next. We offer certification programs for students that are aligned with American Welding Society curriculum, along with National Institute of Metalworking Skills and SACA on the robotics side. We offer that on our own, as well as through Operation Next, which is a program that is near and dear to our heart, which was developed as a program for active duty service members before they leave the service, as they're getting ready to separate from the service 6 months before, allowed to enabled to earn a certification in one of these most in-demand manufacturing jobs, so they can start their civilian career right off the bat, as soon as they leave the service, without any really transition time at all. That program has, after its successful launch and pilot at Fort Campbell, Kentucky, has expanded elsewhere around the country. It is available in the Hampton Roads area of Virginia. It is open to the National Guard and Reserve and their spouses, well, which is important, in states like Michigan, Florida, Wisconsin, Alabama, New York, and more to come. So this program is rolling out around the country as well, as a way to give back to our men and women who served our nation so bravely. I would be remiss if I didn't remind you that we are a membership-based organization. So what do you get after becoming a Lyft member? We get everything you see on the screen here. We are a trusted advisor with all of our in-house expertise, along with the expertise we have throughout our ecosystem, really trying to guide people, guide organizations with the best advice we can to help them make the transition to smarter manufacturing, not selling a specific technology or product, but something that give you the best advice you can to make that transition. We are a technology accelerator, again, taking these ideas and concepts across the valley of death into commercialization is where we live, to help these technologies get into the hands of the marketplace, into the hands of the warfighter as quickly as we can. We're a technology showcase. If you have not been here to our Detroit facility, I certainly invite you to do so. Next time you are in town, please let us know. We'd be happy to show you around and show you all the capabilities that we have here. And then we're a connector and a convener. That's really why we're here today. So thank you everyone for joining, really trying to connect government, industry, and academia to move the needle in advanced manufacturing with some of the brightest minds around. And that includes everyone on board today. A talent developer, we talked about that, trying to develop the next generation of multi-skilled advanced manufacturing technicians. And finally, we are a government partner. I mentioned that is an important role that we play. It can be tricky, it can be unwieldy, it can be challenging, particularly for small to medium-sized companies to begin work with the government. How do they do it? Where do they begin the process? We are a conduit to make that happen. So if you have questions about us, please don't hesitate to reach out. You can follow us on our social media channels. You can give us a call or visit us on our website, or send us an email. I'll be happy to answer any questions that you might have. But with that, I'm going to turn the presentation over to Aaron Nardi, the Chief Technology Officer at VRC Metal Systems, to talk to us about cold spray fundamentals and applications. So Aaron, the show is yours. If you want to share your screen, we are all ready.
Can you hear me now?
Oh, yes, we can. There we go.
Okay. All right. It was on my end. I'm sorry. Something switched.
No problem. The show is yours, sir.
Okay. Sounds good. Sorry about that. All right. So let's get started. What I'd like to do is talk today about, I'll give you kind of an update for those who don't know who VRC is, or an introduction for those who don't already know. Also talk a little bit about process fundamentals, the equipment that's used, especially I'm going to focus on high pressure cold spray here. Little bit about materials and process development, what kinds of properties you can expect from this type of a process. And then I'll show you some applications, and that's where I think you'll get a lot of ideas about what can be done with the process. So to start with, VRC was founded in 2013. Now, leading up to that, there was work between the South Dakota School of Mines and H.F. Webster Engineering Services developing repair technologies for the Department of Defense. This work was done in collaboration with the Army Research Labs. And out of that came a patent between ARL and South Dakota School of Mines on this high pressure hand operable cold spray concept, which is the basis for where VRC started. Now, since then, we've turned into a full service cold spray provider doing more than just the handheld operation. And you'll see that from slides going forward. So today, VRC occupies still our headquarters is in South Dakota, but we also occupy facilities in Webster, Massachusetts. That's where a lot of our research and development, especially materials research, is done. So our headquarters is your engineering, system production, and so forth. Webster is a lot of our research, and then Mid-America Aerotech, which is in North Dakota. That's a former Moog facility. That is a full MRO, and it's an FAA repair station. So that's primarily aerospace parts repair. We also have two facilities for production targeted mostly at the Navy community. So that's one of those is in Chesapeake, Virginia, and the other is in the Puget Sound region. The Puget Sound region is actually just being developed right now. So within 3 to 4 months, that facility should be up and operational, but the Chesapeake facility is up and running today. So like I said before, we're now a full service cold spray provider. So we do everything from the R&D and process development to systems engineering and manufacturing. You'll see a little more about that. We also do integration, booth integration with robots and so forth. We do on-site repair as well. So we'll actually go to a customer site and repair their hardware at the point of need. We do fee-for-service work, and then we even do operations support. So this is for our customers who buy a system, for instance, and then want to get an ROI right away. We actually come on site and operate the systems for the customer for some period of time. All right, so now let me get into what this process is all about, this cold spray process. So we take a compressed gas and we accelerate powder through a supersonic nozzle. And when we do that, we consolidate that material through a severe plastic deformation when it impacts on the substrate. So this is like cold welding, but it's happening at a very, very high strain rate. So this works really well for metals. There's a lot of pure and alloyed metals that have been sprayed by us and by others. This is probably the bread and butter for this process. We also do metal blends with ceramics, for instance. So there's a lot of value in this for wear-resistant materials and so forth. But it can also be used to spray polymers and polymer blends. So it's actually a cold process, which you're going to see, relatively cold process relative to the materials properties. And that's what enables it to spray pretty much anything that has some plasticity to it. The system consists of pretty simple components, a control system, heaters, powder feeder, applicator nozzles. And this is all to get that acceleration of the powder particles, as you see, impacting on the surface and causing severe plastic deformation. When you do it right, you get a deposit that's relatively featureless. But if you etch it, you can actually see that severe plastic deformation within the particles themselves. Now, I said before, this is a solid state process, and that's really important as we start to go forward through the discussion, because unlike your thermal spray processes where your materials tend to melt and then re-solidify when they impact on the surface, these particles are impacting relatively cold, well below their softening or melting points. And that ends up causing severe plastic deformation, which is where kind of all the magic happens. That's where the bonding is occurring, and that's how you're getting good interparticle bonding as well. So where this is occurring, where all this acceleration is occurring, is really in the nozzle. The rest of the system is a way to get the gases at the conditions we want them and the powders at the condition we want them to this nozzle. The nozzle is a converging, diverging nozzle, but just before the nozzle is where the powder is injected. So at that point, the gas is still hot, relatively speaking, and the powders do warm. So there is a component of warming that material that could either be good or bad. So positioning of that pre-chamber and the injection tube, there's several different applicator designs that are used to achieve different preheating distances. Then the gas goes through the converging section, through the throat of the nozzle, and then starts to expand out through the diverging section, which is where the gas goes supersonic and the particles really start to accelerate. So in order to kind of better understand this process, we can figure out what the velocity and the temperature of the particle is at impact, but we need some way of rationalizing what that does on, during consolidation. So there's been some work in doing this. This is an example of some work done by the Helmut Schmidt University to come up with a critical velocity number. This is a semi-empirical formulation that does a pretty good job with a lot of different metals, especially pure metals. So it gives you a sense of how the particle velocity and temperature affect bonding of that material. So we take things like this, we put them into tools like this spreadsheet tool here, and then we can start to look at the entire distribution of powder in the entire distribution of sizes in that powder, and how those different size particles are bonding and building up and so forth. So that's what this is showing. And once you know that, you can then start to understand better what's going on at the impact location. This shows the physics of what's happening. So on the top right, you see a copper particle. This is a very large copper particle, and this impacted at a high enough velocity to bond, but just barely, a little bit lower than this velocity, and particles were bouncing off above this velocity, and we get bonding. And you can see where the bonding starts. The bonding starts at the outside edges of the particle. The very bottom of the particle is actually unbonded. Now, if you look very closely, there were bonds that had occurred there, but they broke apart due to the elastic rebound of that particle. Now, if you look at the bottom left, you can see an aluminum particle impacting on an aluminum substrate, and there's much more severe plasticity. So this is at a much higher velocity. And you can see that the interface is completely consumed, and there's jetting of material outward from that interface. And that's what happens when you get a very good high quality bond, which is what we're looking for. This explains this a little bit better. The upper images show a particle impacting on a surface. That particle creates a jet from the interface, and that jet is what cleans the surface and creates that high quality bond. But another part of this is plasticity. So that the first jet that forms is really from a shock wave. The second jet that forms is from the plasticity of the material itself. So that's down at the bottom right. And both of these are needed in order to get a high quality bond. The shock wave jet cleans the surface, and then you get this high amount of plasticity between the two particles, and that is what gives you your good bond. So when you do this correctly, you can get numbers like you're seeing here. This is testing that we do. It's a shear type of test where we actually build up a we build up a lug of material on this bar, and then we try to shear those lugs actually from the surface. And when we do that, we can get numbers that you can see here, like 22 KSI on a magnesium substrate. So magnesium is, the yield strength of magnesium is in that ballpark in 22 KSI range. So the bond strength is actually just about as high as the yield strength of the substrate itself. Now, we're not quite that close on all the other materials here. You see some steels that are 40 Rockwell C with tantalum on them, for instance, that can be in the 35 to 50 KSI range, still much more significantly higher than like a thermal spray coating would be, for instance, where you can actually use this as a structural member, but not quite as high as the base steel strength itself. So there is you do have to plan the design of interfaces sometimes if you're taking major structural loads through the deposit, but it can be done, and it has been done. All right, so once you figure out the interface, the substrate interface, now we have to also think about the interparticle bonding, because that's where you get your strength from. So this shows kind of two examples. One that was a lower temperature, high velocity spray, which is to the left. And then the image to the right is the nitrogen sprayed, which is going to be higher temperature, lower velocity. And what you can see with these two is much more ductility in the one on the left, which is the helium sprayed, high velocity, low temperature. And if you look all the way over to the right, you can see examples of the FEA models for these two conditions. And you can start to see why we're getting that better interparticle bonding in the helium sprayed condition, for example. So even though the temperature itself brings that critical velocity ratio up to similar values as the helium, the particle itself is where all the deformation is occurring because the particles are so hot. The substrate is not seeing as much of that deformation, and that limits the amount of bonding. So you need plasticity of the particle and the substrate to get that really high quality bond. And when you do that, you can see an example of a strained deposit on the left in these or on the right in these images, and on the left is the unstrained. And this is where ductility really comes into play. So when you build up these materials at very high velocities with lots of plasticity, you actually consume all of the interparticle defects, and that's how you get a high ductility material. So in the top here, you see something that has 3.5% elongation, and you can actually see the defects opening up in the high strain region. You can see pores opening up. In the bottom images, it's a different alloy, and we're able to get up to very high elongation. And in this case, you see very few interparticle defects and significant amounts of strain in the individual particles themselves. This also translates over to fatigue performance, as you can see on the right-hand side of the page here, where going from the blue to the red to the black curve, we're going from 2.5% elongation to 3.5 to 4.5. So you can see the increase in fatigue performance as you get rid of a lot of those interparticle defects that are present in the material. You can also see this in things like conductivity. So this is an example of on the left, we have plastic strain to failure for a 6061 cold sprayed material versus the conductivity from a eddy current test. So this is electrical conductivity. And you can see that there, as you increase the eddy current, or as you increase the plastic strain to failure, the eddy current response is much higher, where raw material is way up there at the top. You know, in some cold spray cases, we're more than half of what the raw material shows. Now on the right, you see copper, and you see it's a similar trend. As you increase the gas temperature at the bottom, or you increase the pressure, which is also that's the difference between like the yellow and the blue is, well, it's first of all, it's air, but it's also higher pressure going to the 30 bar, which is the blue samples. And then you see helium. If you use helium, which is a much higher velocity gas, you can get up to that 99% at even lower temperatures. So there's a profound effect on that conductivity of the material when you increase the velocity of the particles. So in order to get all these effects correct, we actually have to have special powder. Just like every other industry, you want to have powder that's tailored to the process. So that means particle size distribution, but it also means things like microstructure, because this is a cold process, a relatively cold process. So we try to affect the microstructure of the material as well. And we also blend materials, we granulate materials, we do lots of things to get the particles into the right condition so that when we cold spray them, we get these high quality bonds as well as interparticle bonding. So with that, I'm going to get into equipment. The first piece of equipment is really the flagship system that VRC came out with, which is called our Gen 3 system. Now you see here 3 images along the top, where one is somebody hand operating the system. Second one is a robotic, and the third is also a robotic operation. It's more common to do robotic operations. That's where most people are. However, there's a lot of need for hand applied, especially for complex geometries on large parts. So if you're fixing a small complex divot or something on a large vehicle or something like that, it's very easy to do that process by hand. It's a little more complicated if you have to robot program every application. So the second system I'm going to show you is called our Raptor. This system has all the same capabilities as the Gen 3, except we've actually put this into a dust tight and watertight containment. This is made to be able to go onto a ship deck for the Navy, for instance, be able to wheel it over to wherever you want to do your work and do your work, but then leave it out and not have it get damaged. It's also got hoist hooks on the top, and it's got places on the bottom for you to pick it up with a fork truck, so you can move it around all over pretty easily. Now, if you want to really move things around, this is a very small, lightweight unit that is all, it can all be picked up and moved by hand. So it's got the same pressure and temperature capability. It is only a one gas system though. To make this lighter, we actually made this a single gas system, which means you can use any gas you want, helium, nitrogen, air, but you can only use one at a time. Where our other systems, you can actually use nitrogen and helium, so you can start up on nitrogen, switch over to helium, and so forth. This system, though, is small enough that it can fit into the hatch of a submarine, which is what it was originally designed to be able to do. But it's also been ruggedized. These cases are vibration resistant and so forth. So you can take these on a plane, take them to wherever you're doing your work, and use the system. And the last thing I'll show you is, this is a new release for us. This is coming out this quarter, actually. And this is a applicator heater. So with most of our other systems being hand operable, the goal is to have it as lightweight as possible. Now, what that does, though, is it makes the heater a remote device, and then you have hot gas going through a hose to your hand applicator. There are needs for higher temperature at the nozzle, however, and you can get there by going to a direct connection between the heater and the applicator. And that's really what this is designed for. So we've built in things like water cooling of the nozzle as well. And we've kept the entire weight of this device, so that's the heater and the nozzle, the whole assembly, below 15 kilograms, which was a goal of ours in order to make use of many of the thermal spray robots that are out there commonly in thermal spray facilities. So we're trying to keep this as lightweight as possible, but still maintain the high pressure, high temperature. Many other auxiliary systems or products as well, nozzles and glove boxes, portable dust collectors. So these are important, especially when you go to do work on vehicle, out in service somewhere. You need some way to pick up the dust locally, and that's what these things are good for. And we're also doing work with nitrogen generation and air compression systems to supply gas to the process as well. So I mentioned before about integration. This shows a typical booth. This would be a robot, a dust collector, a sound enclosure, as well as the cold spray system itself. We usually use a robot and a tilt turntable, although again, you can do it by hand. You could also just have a robot. And so there's many different configurations, but very commonly it uses a robot with a tilt turntable. We also have much more extravagant integration systems. So the one in the upper left is actually housed in our Webster, Massachusetts facility. This is a cold spray booth connected to a machining center with a helium recovery capability. So when you do need to use helium gas, which is becoming more and more rare, we're finding more ways to use nitrogen to replace helium, but there are still those instances when helium can be really valuable. So when that's the case, you can do something like helium recovery, which is the unit that's shown there in the upper left. Now, these other two systems are more portable integration capability. The first one is a containerized based system. This was just finished really this past month, and it has power generation included. It's got gas as well, and a spray cell, an entire spray cell. The bottom one is a trailerized system, which can be parked right next to a vehicle, as shown here in this image. It's fixing a window frame on a V22. So show you a couple more images of this campsite system. This is the containerized system. So if you look in the bottom left, you can see an image of the generator on the right, and then on the left there's a compressor. So in this case we have a compressed air system on board, so we can do air sprays using this system. And air, we can do most everything that we can do with nitrogen. There are some oxygen sensitive materials that don't work as well with air, but for the most part, air can get us 90% of what we can do with nitrogen. So, you know, in this case, you can get a lot of work done in the field, and you can drop this thing wherever you want. And it's completely self-contained. Now, in the right-hand side is where your actual spray booth is. So you see a person there setting up a small robot. This is a collaborative type robot. And then there's a table to do your work on. Dust collection is actually behind the individual here. And then there's a little hoist to bring parts in and out. And then the upper image shows the control room. And that's where the dust collector physically sits. There's a little oven for heat treating small parts if you need to. And then your control systems are in there as well. This is a new trailer-based system. This is one where there's a deployable platform or cart, which houses the heater and the powder feeder. It's also got these, it's also got feet that can go down to stabilize it, and it's got its own collaborative robot on it as well. So you can drive that over to wherever your vehicle is, and you can do the work on there. Now this also has gas on board, so there's air compression on board, as well as a dust collector, a portable dust collector. So you have a complete cold spray system, plus the gas, plus the dust collector. The only thing you're missing in this case is the power, which would have to be on a separate trailer or from a facility, wherever you're at. So with that, I'm going to talk a little bit about materials and process development. This is going to get into properties of many of these materials. This is an example of an F357 cold sprayed material repairing an E357 substrate. So in this case, you can see the mechanical property differences here. The strength of the cold sprayed material is actually a little bit higher. The tensile strength is a little bit higher, even though the yield strength is a bit lower. But the ductility is pretty close too between the F357 and the E357. So in this case, you know, we're applying a material that's relatively comparable in properties. This gives you a little more specifics about what you can get with helium and with nitrogen. So most of what I'm going to show you is helium, but we did also look at nitrogen. And when you nitrogen spray this same material, you do get a lower strength as well as a lower ductility. From a structural standpoint, certainly in this case, the preferred material would be the helium. Now, if you look at how this material performed in a conventional fatigue test, it's conventional from the standpoint that it's a load-controlled fatigue test. It's a little unconventional from a specimen design standpoint. In this case, we're actually taking a flat panel that's got a blend out in it, and we're repairing the blend area to try to get increased performance over a blended region. So the idea here is that blend outs are already approved by the Navy. This is for NavAir. Blend outs are already approved by the Navy. So if we can get improved properties over a blended coupon, we don't even have to get back to a pristine coupon, but we can just get better properties and we can have success. In this case, you're seeing an order of magnitude increase, and we've shifted the repair or the failure to a fairly random location with the samples on the right. as compared to all of the samples failing right in the middle of the divot on the left. So we've actually brought the samples back to a pristine condition in this particular case. Now, in this case, we have a cold sprayed 7050 material. This is a much higher strength material. The base material is much higher strength. It's a wrought material. So in this case, our cold sprayed material is not quite as strong as the wrought material. However, in the same type of test, we still see an improvement in the mechanical properties. We're not getting an order of magnitude improvement, and we're not necessarily getting up to the strength capability of baseline material without a divot, but we are seeing an improvement in the properties. This is showing some wear and impact resistance materials. So we're stepping away from aluminum and starting to look at nickel with tungsten carbide or nickel with chrome carbide. And you can see dramatic improvements in wear performance over chrome plating in the bottom left. And then on the right, you can see for the chrome carbide nickel, you can see an actual improvement in ballistic performance as well. So this is repairing armor. This is high hard armor repair. And these are V50 type of tests, which means basically the 50th percentile will fail. So half of the samples will fail at that velocity condition. So what you can see here is we're actually getting an improvement when we use helium. We're about on par when we use nitrogen, but even with nitrogen, when you start to look at fragmentation rounds, which is all the way over on the right, we're seeing actually a significant improvement in the performance there. So with armor piercing rounds, we're on par when we spray with nitrogen, but with fragmentation type rounds, we've actually improved over what the baseline steel was capable of. It's also possible to spray metals onto polymers and also polymers onto polymers and so forth. Again, anything that has plasticity in it, we can spray, and we can combine a lot of different materials together. Another interesting case is the use of copper for antimicrobial coatings. So there's been a lot of work done in taking copper in general and using it as antimicrobial. It's even better when you cold spray it, though. You could see here an example of 3 different coatings on the left. These are 2 thermal spray coatings and a cold sprayed coating. And this is the survival rate of MRSA bacteria. So here you see a significant reduction in the survival of the MRSA on the cold sprayed material in comparison to the others. On the right, you actually see influenza A virus. Similar thing, you can see a dramatic reduction in the cold sprayed copper over just wrought structural copper. And this has to do with the severe plasticity that we put into the material causing dislocations. So you get a high dislocation density, and that actually enables the ion transport within the material, which is what gets you your killing properties of these viruses and bacteria. So cold sprayed copper, even better than regular copper, which is far better than most other surfaces. All right, I'm going to end here on applications. The vast majority of applications that we get have to do with repair, and those are typically for corrosion or wear. Those are the most common applications we have. We also do some with structural repairs, structural addition, feature addition, and we even do additive manufactured parts. All this is possible with cold spray, but like I said, the vast majority of work today has been done on repair of corrosion and wear damage. These are the type of deposits that you can get. The upper left is a pure metal material. Then you see some blends that have carbides in them and so forth. Down at the bottom right, you see a very lubricious bronze material. And then you see a layered structure in the bottom right, which has a layer of chrome and a layer of niobium and so forth on a steel substrate. So you can do coating, different coatings together as well with two different powder feeders. You can switch from one to the other and start spraying the second. So there's been a wide variety of applications. I'm not going to go through every single one of them, but there's been a whole bunch in the aerospace industry. That's the industry that really took hold of a cold spray first. And that's because of the high value parts. And a lot of these were actually aluminum parts, which is very sprayable with cold spray, with the cold spray process. So there's been a lot of repair work done, a lot of different applications for the aerospace community. Just to show you a couple of them, here's one where a magnesium gearbox, this is a reduction gearbox for this PT6 engine. And in this case, the one that was given to us for repair, to qualify the repair, actually had through wall defects. So you see a hole through the part here that was able to be filled in and repaired. So the bottom here, you can see the repaired part. And then two more were done after this that were much less severe. This was the most severe damaged one that was used for qualification. Here you can see the application of a Babbitt material for a propeller system. So this is a bearing for a propeller, and there's Babbitt was worn and it needed to be added back on. So here's an application where we can add that Babbitt back in place. And then here's an example of a hard coating repair. This is a nickel chrome carbide repair of a steel part. So this happens to be a check valve, for aerospace in a bleed system. But in this case, this damage on the upper left, the damage to the flap is not supposed to be there, and that's the main work that was done. But also the end face here of the pivot was sprayed as well. All right, so here's an example from a Navy application. So this is a highly corroded part, as you can see. There's two of them. The one on the left is a TD16, and the one on the right is a TD63 actuator. Both of them are aluminum. They're both repaired with 6061 in this case, and then finished to the final condition. This is an example of a bronze repair. In this case, this is a very large part. This is a very large and very expensive as well. It's a main circulating pump for an aircraft carrier. And this part costs a significant amount. It's about $500,000. So in this case, we had to put about 30 pounds of material back onto this part. And that took about 2 weeks to do the full turnaround to complete that. So that's preparation, path planning, and spraying, all that work in about 2 weeks. There's also been some work done. This is courtesy of Penn State, you can see there. This is some work that's been done on doing repairs actually on ship with magnetic robots. So this is a small robot that can travel around and repair the surface of a ship. So this has a grinder on it, as well as the cold spray system. So you can prep the surface as well as repair the surface. I also wanted to throw in something on ID applications. I didn't have a lot of slides on that, but it is possible to use very small ID nozzles and actually be able to repair the insides of a part. So this is a large kind of keyway in about a 3-inch bore. and we're repairing that keyway, and we're also repairing the internal diameter itself. So you can see that all filled in, and it's not finished machined yet, but it's ready for finished machining in the bottom right. Wide variety of applications in heavy industry, some of which we've already attacked and we've already worked on, some of which we haven't. And then there's also, for heavy industry, a lot of that's wear coatings. So those are a lot of those carbide coatings. This is really our corrosion protection materials. So you can apply things like aluminum, as well as dense like nickels and things like that, stainless steels. So you can either create a barrier or you can actually provide galvanic protection. And we've also worked on developing wide area nozzles as well, so you can spray larger areas quicker if you're just trying to put a thin coating of a galvanic protection down, for instance. And the last thing I'll leave you with here is additive manufacturing. There's a lot more to say about additive manufacturing, but that would be a talk all of its own. There's really two ways you can do additive with cold spray, and we've done both. The first is to actually build layer by layer on a platform like you do with most other additive processes. The other thing is to actually build on a mandrel. This is a very nice way to make certain shaped parts. So in this case, you see an airfoil type shape that was created on a mandrel on the bottom here. So this is a titanium airfoil shape that's being made on a aluminum mandrel, and then the aluminum mandrel is eliminated afterwards. There's many different ways to make the mandrels, but the idea here is to basically create that shape by creating a mandrel with that reflects the shape of the final part that you want. And with that, I'll leave my contact information up here for anybody who wants to get a hold of me. We also have our web pages there for VRC as well as coldspray.com. Feel free to reach out or to go to one of those sites and see if we can answer any questions. Are there any questions from the audience?
Yeah, awesome. Thank you. Thank you very much. We have a couple of minutes for questions. And we had a couple of some technical difficulties earlier. So we'll try to go through these as quickly as we can. What is the process loudness at the nozzle in terms of decibels?
Sure. So at the nozzle, you're probably talking about, you're above your 85 decibel threshold, which is why we use a sound enclosure. So it really depends on the nozzle and the process condition you're using. It can be, I've seen it measured anywhere from 90 to 115 or so. Obviously larger nozzles, more gas, you're gonna hear, a louder noise. However, when we do work out in the open, we can actually have attenuation of the sound with just simple blankets around the process. And obviously the operator, if we're doing handheld operation, has to wear hearing protection because he or she is close to the actual nozzle itself. Oh,
Thank you for that. What are the compressed air or moisture cleanliness requirements?
So generally from a moisture standpoint, we like to keep it very low. So we like to be in the tens, single digits to tens of parts per million of moisture, which, your bottled gases are probably around 10 parts per million, a lot of your bottled gases. So, I mean, we've seen anywhere between 10 and 100. That works really well. You start to get too moist and you will see, problems in your deposits. That's the much bigger issue. If you have nice dry gas, you should be in pretty good shape. You definitely don't want a lot of contamination from solid materials in there, like rust and things like that. So if there's anything like that in your system, you'd want to filter it out. And that's mostly for the control system itself, your mass flow controllers and so forth. We don't want to put a lot of that sort of debris through those.
Got it. Thank you. And probably one more. Did you mention what software you use for your FEA simulations?
Oh, there's been a few different models run. Most of the ones that I'm familiar with have used Abacus, but there's been some ANSYS models. And then there was another, I know there were a couple that were SPH models as well. I don't know what software packages those were done in though. So there's been a lot of different universities using different models. We haven't done a lot of the impact modeling itself in our company. We typically use ANSYS, but we don't do a lot of that impact modeling. A lot of our university partners do that.
Okay, got it. And I said one more, but now I really mean one more. What are the health and safety constraints about spraying inside a building? What precautions are there, if anything?
So this is a lot like a thermal spray process. The only major difference is you're not using any kind of explosive gas, but you do have to still deal with metal powders. So you want to manage that with proper dust collection, cleanliness of your booth, cleaning up at the end of the day, all that kind of good stuff. So all of those metal dust handling apply just as they would with any thermal spray process. So it's a very common thing to do in industry. We've built many of these systems. A lot of that's local. As far as approvals go, a lot of this happens locally. So that's every location is a little bit different. So.
Awesome. Well, thank you so much. I know we are at the top of the hour, maybe 1 minute over. So I want to thank you for your time. Thanks for the presentation today. Certainly appreciate that. I'm looking forward to learning more and seeing more as we continue to grow and get more involved with cold spray, and look forward to having you as a partner with us along that way. So thank you very much, Aaron, for that. If anyone has any questions, further questions, I know there were some questions we didn't get back to. We will make sure that we get those to Aaron to follow up with afterwards. You can direct them directly to Lyft as well. So thank you very much for joining us today. You can join us next week at noon as Solvis Global provides another liftoff webinar as well. But in the meantime, thank you very much for joining today. Thank you, Aaron. We appreciate you, and hope everyone has a great rest of the day.
All right. Thank you.
Thank you.